Welcome to the Signal Tap Logic Analyzer online training. My name is Steve. While watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. By the end of this training, you will understand the many advantages of using the Signal Tap Embedded Logic Analyzer for debugging your FPGA designs. You'll see just how easy it is to add the logic analyzer to your designs and configure it for your unique debugging needs. You'll be able to take the signal data captured by the logic analyzer, analyze it, and use it for further debugging, for documentation purposes, or to get a better understanding of how your design works. Finally, you'll learn about some of the additional features of the ELA that go beyond the standard system debugging flow, but help make the task of verifying and debugging designs even easier. Here is the agenda for this 4-part training. Part 1, which you're watching now, starts with an introduction to the Signal Tap Embedded Logic Analyzer, summarizing its features. The rest of Part 1 can be used as a quick start guide for implementing and using the logic analyzer. We'll look at the debugging flow for integrating a Signal Tap instance into a design and using it to debug that design. This includes how to create Signal Tap instances, add tapped signal nodes to the tool, compile, and run the design that includes the logic analyzer in an FPGA device. Subsequent parts of this training, available on the Intel FPGA training website and linked at the end of this training, provide more detail on the tool, including how to define basic trigger conditions and configure the many options available for the logic analyzer. You'll also get more information about compiling and recompiling a design that includes the logic analyzer and programming a device with that design. You'll also learn about advanced triggering options that you can use to capture those hard-to-catch signal events. Finally, we'll look at the many additional features available in the tool to help simplify the debugging process. Let's get started with an introduction to exactly what the Signal Tap Embedded Logic Analyzer is and how it works. How would you typically debug the functionality of an FPGA design in system? Well, you'd start with a board that includes the FPGA device and test equipment you would use to debug the design on that device. In order to monitor internal signals, the FPGA design must have available I/O pins and physical routing channels for routing out the signals you want to monitor. The Intel Quartus Prime software signal probe or logic analyzer interface features can make this process easier. After programming the device, you attach probes from the test equipment to probe points on the board for the desired signals. Overall, this can be a good method for debugging a design. This setup has the advantage of debugging at a system level, giving you an overall picture of everything the FPGA is connected to. External test equipment typically has large amounts of buffer memory for storing large quantities of data samples. These devices also have many options for specifying what data to capture and when to capture it. This gives you great flexibility in how you debug your system. However, there are a number of disadvantages. Any signals you want to monitor must be physically accessible on the board to allow for attaching a probe to the signal. This requires extra planning for the board design, including the addition of built-in test pads, headers, or connectors to allow for connections to all the signals you expect to monitor after the board is built. If you later realize that there are additional signals you need to monitor, a new board must be built. Even if a signal is successfully brought out, there is always the possibility that a device probe or other board component could affect signal integrity or timing on critical signals. Even just the routing of such signals to a device I/O pin can affect the signal's behavior. While high-quality test probes can help prevent this, they can be very expensive. Once all these issues are taken care of, you can finally configure and use the test equipment to capture the tapped signals. So, what is the Signal Tap Embedded Logic Analyzer, and how can it help debug functional issues in your designs? The ELA basically takes the brains and features of a typical external logic analyzer and incorporates them into your FPGA design, programmed into the target device on your board. It is an embedded logic analyzer built using available FPGA resources. No I/O, board routing, or probe points required. The Signal Tap Logic Analyzer emulates many of the features of an external logic analyzer. It taps signals within your design, meaning it samples, captures, and stores on-chip internal signal data values. This is done on the rising edge of a specified sampling clock. SignalTap gives you the unique ability to monitor deeply buried design signals in real time during normal system operation. You're able to control and view captured data on the fly through a standard JTAG connection, typically used for programming the device, or, in some cases, remotely over a network. The SignalTap ELA is available for free and included automatically with a standard installation of the Lite, Standard, or Pro editions of the software. A version of the SignalTap control interface is also included with the standalone programming software, allowing you to control and monitor the ELA without a full installation of the Intel Quartus Prime software, though without the ability to reconfigure its settings. You can find this at the Intel FPGA Download Center. The logic analyzer is created in the target device using unused logic elements and memory blocks. To illustrate how it is implemented, here is an FPGA device programmed with a design. One or more instances of the SignalTap logic analyzer are added to the design, each with its own buffer built from available device memory blocks for storing captured signal data. Each instance is configured to tap desired signal nodes for monitoring or for defining triggers, the condition checking performed by the tool to determine when to capture data samples of the tapped nodes. The JTAG connection programs the device as well as controls the operation of the SignalTap instances after device programming. After data is captured and stored in the logic analyzer's memory buffer, the data is transferred to the PC for analysis over the same JTAG connection. Based on how the logic analyzer works and how it is implemented, it's easy to see when you might want to use it and when you actually can use it. If you don't have any external test equipment available, such as multimeters, oscilloscopes, or logic analyzers, the SignalTap Logic Analyzer is a great replacement. As mentioned, you need available logic blocks to implement the logic analyzer itself, and you need memory blocks to store captured data samples. In most cases, you must have a direct, active JTAG connection to the device under test to control the logic analyzer. Typically, this makes use of an Intel FPGA download cable. However, if your design includes a network connection, remote access for debugging over a network may be possible. We'll look at these additional connection options later. One of the most important details to understand about debugging with the ELA is that you can only perform a functional debug. Any timing delays inherent in the design will not appear in the captured data. This makes sense since data is only sampled on the rising edge of the sampling clock, hiding any timing information that may occur at other points in the clock cycle. It's helpful to look in a bit more detail about how device resources are consumed by the logic analyzer. SignalTap uses device logic elements and memory block resources for its implementation. However the logic analyzer is configured, it must fit in the device along with the main design being tested. The amount of logic required is based on the number of signals or channels monitored, as well as the number and complexity of the trigger conditions. The amount of memory used is determined by the number of monitored channels as well as the sample depth, meaning how many samples are captured and stored in the memory buffer for each channel. The more channels monitored and the deeper the sample depth, the more memory blocks are required to implement the logic analyzer. In theory, for each instance of the logic analyzer, you can capture up to 2048 channels with up to 128K samples of each channel. However, An ELA of this size would require 13,107 M20K blocks to store all the captured data. Even the largest Intel Stratix 10 device has only about 11,000 M20K blocks. Thus, you can make a logic analyzer instance as big as needed, but you will probably be constrained by the size of the device before you get anywhere near maxing it out. Later, we'll look at the storage qualification feature, which lets you make the most efficient use of the limited buffer space available in a device. In the standard edition of the Intel Quartus Prime software, as you make changes to the logic analyzer configuration, a resource usage estimator constantly updates to keep track of the number of resources required. This helps identify if you need to simplify the tool's configuration because your device is running low on available resources. Here is a summary list of the main features of the Signal Tap Logic Analyzer. The ELA provides the ability to debug multiple clock domains simultaneously by instantiating multiple instances of the logic analyzer in one project and controlling them all through a single interface window. As already mentioned, the tool lets you capture a large quantity of sample data for as many channels as needed, limited only by the availability of device resources. For triggering options, the logic analyzer can monitor up to 10 different trigger conditions sequentially or in any order you choose with the state-based triggering feature. The external triggering features make it easy to interface the logic analyzer with other devices or logic, including the hard processor system on SoC devices. The trigger conditions themselves can be basic Boolean AND or OR triggers, or advanced triggers in the form of more complicated Boolean expressions. The Signal Tap Logic Analyzer makes it easy to create almost any type of triggering condition. To make effective use of limited buffer space, you can enable data storage qualification. With this feature, captured data samples are either stored in the buffer or dropped depending on selected conditions. Finally, the data captured by the logic analyzer can be stored in many formats and exported for use in other applications such as simulation, power analysis, or design documentation. We'll discuss most of these features in this training, but check the Intel Quartus Prime Debug Tools user guide and the Intel FPGA website for more details about these and other features of the tool. Links to these resources will be provided later. Since the Signal Tap Logic Analyzer is integrated directly into your FPGA design, it is helpful to define a task flow to help understand the way this integration should take place to provide the most benefit for the debugging process. You start with a new or existing FPGA design. When starting with a brand new design, it's a good idea to prepare for the integration of the logic analyzer later by allocating device resources for its use. It might be difficult to add the logic analyzer later in the design process. In the design, one or more instances of the logic analyzer are added. Each instance is configured as desired for the target device and the appropriate debugging situation by selecting signals to tap and specifying properties of the sampling buffer. Once an instance is configured, trigger conditions can be defined. These three main tasks can be repeated in different orders during the debugging process, so we'll group them together in the create and configure stage of the task flow. Once the instance or instances are properly configured, the project is compiled if necessary. Compilation or recompilation is required when the logic analyzer is first added to a project, or if certain changes have been made to the logic analyzer, such as the addition of a new signal to monitor. Some basic changes made to an existing Signal Tap instance, such as disabling individual trigger conditions, are runtime reconfigurable, avoiding the need for a recompilation. Later, we'll look at ways to reduce compile time if a change requires recompilation of the logic analyzer. When compilation is complete, the target device is programmed using the device's JTAG interface. Once the design that includes the logic analyzer is programmed into the device, it can be run and controlled through the JTAG connection or through a remote connection if available. When the trigger condition occurs, the logic analyzer stops and the captured data is transferred to the SignalTap file window, where it can be viewed, analyzed, saved, or used to locate a bug in the design. If the bug is found and fixed, the debugging flow is complete and the logic analyzer can be removed from the design if desired. If not, the logic analyzer can be reconfigured or the trigger conditions adjusted to try looking for the problem again or to look for other bugs. All the procedures mentioned in this training will fit within one of these main tasks. Now that you understand how the ELA gets integrated into the FPGA design flow, let's see how to add an instance and configure it in the Intel Quartus Prime software. There are two ways to add the logic analyzer to a project. The first way is to create a SignalTap file with the file extension .stp and enable it in the project settings. This is the easiest way to implement the ELA and is recommended for most debugging situations. Once a file is created, multiple SignalTap instances can be added to and controlled with the single file. When the file is saved, it gets automatically enabled for the currently opened project. The file can be edited, enabled, or completely disabled and removed from the currently open project in the SignalTap project settings. The other way to add the logic analyzer is to create it as an IP instance using the IP catalog and IP parameter editor. The SignalTap IP core is called Altera SignalTap 2 Logic Analyzer and is found in the Basic Functions category of the IP catalog under Debug and Performance. The IP parameter editor for the logic analyzer allows you to adjust all the basic parameters needed to create a single SignalTap instance. The resulting output from the parameter editor then needs to be either instantiated in the design with the signals to tap specified in the port mapping or added as a component in a platform designer system design. The ELA implemented in this manner can be controlled from a command line or by creating a related .stp file using the option shown. Removing the logic analyzer from the design requires removing the IP instantiation and recompiling. If you would like more information about implementing the SignalTap logic analyzer using this method, see the Debug Tools user guide. Creating the .stp file alone is, in general, a faster and easier way of implementing the ELA. So this training focuses exclusively on SignalTap usage with the .stp file. Creating a new SignalTap file is simple. You can select SignalTap Logic Analyzer from the Intel Quartus Prime Tools menu, create a new file and select SignalTap Logic Analyzer file from the Verification Debugging Files category, or click the SignalTap Logic Analyzer task in the Tasks pane. The default name for a new SignalTap file is stp1.stp. Use Save As from the File menu to rename the file if desired. As you go through this training, you'll notice that features specific to the Lite and Standard editions versus the Pro edition of the software will be highlighted. The first of these Pro-specific features to note is the option to use a template. When creating a new .stp file, a template can be selected to begin the configuration of a SignalTap instance. This includes setting up or enabling certain features or creating useful trigger conditions. If you want to create the .stp file from scratch, select the default template at the top of the list. Once you've created and configured a .stp file, the window for that file will look something like this. The main SignalTap file window has several different panes, each with its own function. With the Setup tab selected, as shown here, the panes appear as shown. We'll look at the Data tab later. Each pane has a number of different settings and configuration options. We'll discuss each of these panes in more detail as we progress through the rest of the training. Let's start with the Instance Manager. The Instance Manager includes controls and indicators to work with individual or multiple SignalTap instances. The highlighted instance or power-up trigger in the Instance Manager is the active instance. Changes to the settings in other areas of the SignalTap file window only affect the active instance. To switch to an inactive instance, double-click the instance in the Instance Manager or use the Instance tabs at the very bottom of the SignalTap file window. To quickly create new instances, right-click anywhere in the Instance Manager and select Create Instance. You can rename instances by either clicking on the instance name or right-clicking and selecting Rename Instance. For each instance, the Instance Manager indicates the current status of the instance and, in the Intel Quartus Prime Software Standard Edition, an estimate or actual count of the resources used by the instance. Memory buffer resources are organized by size. The tooltips shown here indicate what is considered a small, medium, or large memory block type, but the actual type used depends on the types available in the device targeted by the design. A warning will appear in the resource usage columns if there is a potential for the design to not fit in the target device given the current settings for the logic analyzer. The status column during logic analyzer configuration will always be not running, but that will change later once the logic analyzer starts analyzing and capturing data. The health monitor at the top of the Instance Manager indicates the overall status of all SignalTap instances and whether a recompilation is necessary to integrate updated SignalTap instances into the design before they can be run. Finally, the analysis control buttons next to the health monitor control how each instance is run to watch for the triggering conditions. We'll look at these controls in more detail later. The node list on the Setup tab in the SignalTap file window is used to select signals from your design for monitoring, as well as for constructing the actual trigger conditions. To tap a signal, simply double-click an empty area of the node list to open the standard node finder. Bus groups added to the node list can be expanded, as shown here, to change settings for individual signals within the group. Even if signals are not part of a bus, you can create custom groups in the node list for organizational purposes or to create trigger conditions based on the different groups. Just select the signals you want to group by Shift or Control clicking them, right-click, and select Group. You can also organize signals any way you want and move signals into existing groups through drag and drop. We'll look at what you can do with grouped signals later. The standard node finder found throughout the Intel Quartus Prime software is used to select signals for use by the ELA. When accessed in the node list, the SignalTap specific filters should always be used. The two main filters to use are SignalTap pre-synthesis and SignalTap post-fitting. We'll look at the other filters later. The SignalTap pre-synthesis filter lists signals available after running analysis and elaboration on the project. Analysis and elaboration is the very first step in the synthesis process. It analyzes your design files for correct syntax and sets up the project hierarchy. Selecting signals for tapping with the pre-synthesis filter is similar to creating the connections to SignalTap directly in your design files without having to edit any code. Analysis and elaboration doesn't take very long to run, so this is a quick way to tap signals in your design. Any pre-synthesis signals added to the SignalTap file are available for all basic and advanced trigger conditions. When a pre-synthesis signal is added to the SignalTap node list, it will appear in black text. The second main filter in the node finder is the SignalTap post-fitting filter. The post-fitting filter lists signals that are available after both synthesis and fitting and their related optimizations are complete. These are nodes that have not been optimized away by the compiler. Connections from SignalTap to post-fit nodes will only be made if there are available routing channels, similar to the incremental routing performed with signal probe, if you are familiar with that tool. Post-fit nodes are easily identified by their names in blue text in the node list. If a design that includes the logic analyzer was recompiled, it's possible for tapped signals to no longer be available because of source code changes or design optimizations. If this happens, the signal name will appear in red text in the node list. Signals in red must be removed or replaced before the project will successfully compile with the logic analyzer enabled. To avoid this issue, or to guarantee you can tap desired signals from the post-fit netlist, you can preserve RTL signals through the compilation and optimization process by using Preserve for Debug assignments. We'll look at this feature in Part 3 of the training. You can have a mix of pre-synthesis and post-fit nodes in the node list, as seen here, easily differentiated by their coloring and, in the Pro Edition, their value in the tap column. You can filter the list to view only tapped pre-synthesis or post-fit nodes using the highlighted button. Another way to find nodes to tap is by finding them in the Technology Map Viewer. You can use the Graphical Technology Map Viewer to search the design's post-fit netlist for post-fit nodes to tap. Right-click a node or a group of selected nodes in the Technology Map Viewer to add the selected nodes to an existing signal tap file or to create a new one. As mentioned, it is recommended to use the special signal tap filters in the Node Finder or cross-probe from the Technology Map Viewer. Using these methods guarantees that a selected node can be tapped, meaning that the node is tappable. The post-fitting filter in the Node Finder only displays tappable nodes, which include register ports as well as combinational logic ports if a routing resource to that logic is available. However, there are certain nodes in the post-fit netlist that are completely untappable. These include output pins, signals that are part of carry chains, the JTAG interface signals, as well as nodes that are the outputs from an LVDS SerDes block and within some encrypted IP. Signals in hard IP, like the data and strobe signals in an external memory interface, also cannot be tapped. You might not think that output pins are untappable. However, since there are no direct routing channels from the device I/O elements back into the device for connecting to the logic analyzer, output pins are considered untappable. To tap outputs, find the output signal that drives the output pin and tap those nodes instead. Use the Technology Map Viewer to look at the post-fit netlist, find the output registers or logic that drive the output pins, and add them to the Signal Tap node list. After signals are added to the node list, you can configure how the logic analyzer should use those signals. The Data Enable and Trigger Enable checkboxes on each row in the node list are used to disable usage of the associated signal or group. If Data Enable is disabled, the corresponding signal or group will not be monitored or captured when the logic analyzer is run. This can help in reducing the size of the memory buffer needed by the logic analyzer, since no memory is required for storing sample data for the disabled signals. The disabled signals can still be used as part of a trigger condition definition. If Trigger Enable is disabled, the corresponding signals cannot be used as part of a trigger condition definition. This can help reduce logic resources used by the logic analyzer. As signals are disabled for data or triggering, the resource usage estimator updates in the instance manager to give an indication of the logic and memory savings obtained through the changes. If the signal tap configuration uses more logic or memory blocks than are available in the target device, the overuse will be highlighted in the instance manager as shown here. Disable Trigger Enable or Data Enable options, or remove nodes from the node list to reduce the number of resources required to implement the logic analyzer. All other basic configuration of the logic analyzer is performed using the Signal Configuration section of the SignalTap file window. The Signal Configuration Pane is where you specify a sampling clock, set the characteristics of the selected instance's memory buffer, and configure the use of triggers. You can configure these options either before or after you've tapped signals and set up trigger conditions. If you have used external test equipment before, such as oscilloscopes or logic analyzers, some of the settings configured here should be familiar. We'll look at these settings in more detail in Part 2 of the training, but at a minimum, a sampling clock must be selected. Use the highlighted Browse button to open the Node Finder and select a sampling clock for this instance of the logic analyzer. Now that the basic setup for the logic analyzer is complete, you can finish setting up your SignalTap instance and start capturing signal data. Let's look at how to compile the ELA into a design and run the tool. When a .stp file is first saved, it is automatically enabled in the currently open project. To enable or disable a SignalTap file for a project, go to the SignalTap Logic Analyzer settings in the Settings dialog box found in the Assignments menu of the Intel Quartus Prime software. Disabling SignalTap is a quick way to remove all SignalTap instances from a design, though you will need to recompile the project to completely remove them. If you have multiple .stp files, you can change which file to use with the current project. Also in the settings, you can enable the Preserve for Debug feature. This feature guarantees that nodes you specify will not get optimized away during compilation, allowing for easy addition to the SignalTap node list. The option here in the settings lets you easily disable this preservation for all indicated debug nodes, allowing the design to be optimized through recompilation after functional debug is complete. We'll look at preserving nodes for debug in more detail in Part 3. Before compiling any project, you need to set up timing constraints in one or more .stc files. If your design includes a JTAG-based debug tool, like SignalTap, you should add timing constraints to your .stc file for the JTAG interface. You can do this relatively easily using the highlighted template available from the Intel Quartus Prime software text editor when editing a .stc file. The template is documented in the Timing Analyzer Cookbook linked here. Add the template to your .stc file and customize it for your own use. Once the .stp file is enabled for the project and you've created timing constraints for the design, simply run a full compilation to include the logic analyzer in the design. When you do this, additional design entities are added to the project. The entities listed here will be added to the project and can be seen in the project directory. These entities implement the SignalTap logic and buffers for all SignalTap instances, as well as establish the connection to the device's JTAG hub. Since the ELA uses the standard JTAG connection also used by the Intel Quartus Prime programmer to control its operation, the SignalTap file window can be used for device programming. The JTAG chain configuration pane in the SignalTap file window has similar controls to the programmer. Set up the hardware connection, scan the JTAG chain for devices, and select a device on the chain for programming if more than one device is connected. Once the JTAG connection is established, select the .sof file generated from the project compilation and program the device. You can perform device programming from a full installation of the software or with the standalone programmer download, available from the Download Center as mentioned earlier. It is possible to debug multiple devices on the same JTAG chain at the same time. To do this, multiple .stp files are required, one for each device on the JTAG chain. Program each device using the programmer or the JTAG chain configuration pane in each SignalTap file window. Since the SignalTap file is separate from a design, It is not necessary to open the entire design project for each device. Any .sof file can be selected for programming, but the SOF file you select must be compatible with the current settings in the .stp file for you to be able to control the logic analyzer. In other words, the hardware implementation of the logic analyzer when the device is programmed must match the node list, trigger conditions, and other settings specified in the .stp file. You can guarantee compatibility by expanding the SOF manager with the highlighted button, right-clicking and selecting Attach SOF File, or clicking the paperclip icon if a file has already been selected. Once a .sof file is attached to a .stp file, you can move the .stp file to a different location and use it to program the device without the original .sof file. The SOF manager indicates whether an attached .sof file is compatible with the instance or instances currently configured in the .stp file. The SOF manager works with the data log, a tool for tracking .stp configuration changes and capture data to make it easy to check compatibility as you switch configurations, all within a single .stp file. We'll look at the data log later. When describing the operation of a logic analyzer, the terms run or running are often used. Running the logic analyzer means to start its monitoring of trigger-enabled signals, looking for the combination of signal states that satisfy the trigger conditions. This is also sometimes referred to as arming the logic analyzer, a term often used with external test equipment. All operation of the logic analyzer is controlled by 4 buttons in the instance manager. Select a compiled and ready instance in the instance manager to make these buttons available. The Run Analysis button starts a logic analyzer instance's monitoring for the trigger conditions. If multiple instances exist, you can run them all simultaneously by Shift or Control clicking the desired instances and clicking Run Analysis. The Stop Analysis button does exactly what it says. It stops the logic analyzer from continuing to look for the trigger conditions. You may want to use this if the trigger conditions are not occurring. The data samples currently in the buffer will be displayed when you stop the analysis. Auto Run Analysis behaves similarly to the Run Analysis button, except that the logic analyzer keeps running even after the trigger occurs. The data display gets updated every time this happens, providing a continuous update on the status of the monitored signals. Again, you can stop the analysis at any time. Finally, the Read Data button transfers any captured data from the buffer on the device to the signal tap file. This is used if, for some reason, data is not automatically transferred or the JTAG connection was lost temporarily. When the trigger occurs, the captured data is stored in the memory buffer, transferred to the signal tap file, and displayed in the Datatab. The Datatab is the main interface for immediately viewing captured data. The logic analyzer will automatically switch to the Datatab when data is transferred from the buffer, so even if the trigger did not occur, you can still view what was in the buffer when the logic analyzer was stopped. By default, the horizontal scale of the display indicates buffer sample numbers, one for every rising edge of the sampling clock. You can right-click the scale and select time units to display actual time delays between captured samples. When viewing sample numbers, the sample captured at the trigger is considered sample 0, and pre-trigger data samples captured in the buffer before the trigger occurred, have positive numbers and are displayed to the right of the trigger. Post-trigger samples have negative sample numbers and are to the left of the trigger. If the viewing of data discontinuities for storage qualification is enabled, a feature we'll look at later, extra markers are displayed to indicate where samples were skipped from being stored in the buffer. By default, the Data tab provides a waveform display of all the data-enabled signals in the node list, grouped signals have data displayed in a radix of the user's choosing. You can change the radix or view the grouped signal data in different ways, such as a bar or line graph, by right-clicking on the signal group name in the column on the left and selecting a View option. Controls in the Data tab make it easy to move around the captured data quickly. The trigger position is indicated by a dashed line located at data sample 0. Everything in the waveform display is referenced to the master time bar, a thick black bar that is initially placed at the trigger position but can be dragged anywhere in the data. The numbers above the master time bar indicate the current segment in a segmented buffer and the current sample within that segment. We'll look at the use of a segmented buffer later. The previous and next transition buttons will move the master time bar to the next or previous transition of a selected signal. One or more reference time bars can be added to the display by simply clicking at the top of the view. Reference time bars indicate their location with respect to the master time bar. The top number indicates the segment difference between the master and reference time bars in a segmented buffer. Reference time bars can be used to measure the time between signal transitions or certain events. Left-clicking a waveform zooms in to make it easy to see individual samples. Right-clicking zooms out. If the trigger sample is not visible because of a zoom-in operation, select Center Waveform on Trigger from the View menu to shift the trigger sample to the middle of the display. The captured data can be exported to the multiple file formats listed here for use in other tools or for documentation purposes. Export the captured data using the Export command in the Signal Tap or Intel Quartus Prime file menu. A different way of viewing the captured data is through the creation of a list file. A list file is a simple text file where each row corresponds to the signal states of all the signals within a single captured data sample. The key at the top, along with the columns and column headers, indicate what the signal level is for a particular signal within a particular sample. This makes it easy to see the raw captured sample data generated by the logic analyzer. So to finish up this introduction to the tool and quick start guide, let's review the basic steps in using the Signal Tap Logic Analyzer. First, create a .stp file, adding to it the nodes you want to tap and the nodes to use to build trigger conditions. Create your trigger condition or conditions and specify a sampling clock and other options for the logic analyzer. When you save the .stp file, it gets added to your Intel Quartus Prime project. Compile the project and program your target FPGA device. Finally, in the Signal Tap file window, run the logic analyzer instance or instances and analyze the acquired data. Subsequent parts of this training will go into more detail and highlight some additional features of the tool. This concludes part 1 of the training. If you'd like to continue the training, you can register for and view parts 2 through 4 for free at the links shown here. To learn about additional resources available to help you with using the Signal Tap Embedded Logic Analyzer, continue to the next slide. For more information about the Signal Tap Embedded Logic Analyzer, be sure to read the Signal Tap chapter in the Intel Quartus Prime Software Debug Tools User Guide. Both the Standard and Pro Edition versions of the guide are linked here. If you'd like hands-on experience with the Logic Analyzer, enroll in the Intel Quartus Prime Software Debug Tools instructor-led training. Besides discussing several other tools that help in verifying a design in hardware, you'll get to work with the Signal Tap ELA on an Intel FPGA development kit with direct assistance from an Intel FPGA training engineer. Intel offers many options for learning about our FPGA products and for training on their use. The Intel FPGA YouTube channel contains a number of 5-minute quick videos along with longer, more in-depth training. The Intel FPGA training website is the place to go to learn about our recommended curriculum for every type of user and to register for a class. While there, You can register for over 300 e-learning courses made up of narrated slides presented in an interactive player, some of which include labs and demos. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person at a local office or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Intel FPGA provides many self-help resources. Check out the landing pages accessed from the main Intel website that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Intel FPGA application engineers. One more thing. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Feel free to email fpgatraining@intel.com with any thoughts or comments, positive or negative, you may have on this training course. Thank you for your feedback. My name is Steve, and I want to thank you for taking this online training about the SignalTap Embedded Logic Analyzer.